begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Just ask you to bless our work, help us to understand a little bit more about Lie Algebras. Lord, in your name I pray, Lord Jesus. Amen. All right, so let me just recap what are we up against here. So we got Lie Algebra, and we were talking about definition L solvable. If what? If for some m greater than or equal to 1, you have that the mth derived series is 0. And here, our definition, right, was that L prime was L1, and that was what? That was the span of the commutators, right? So you take the span of commutators from L, that's the derived, and so this is called the derived series. And like iteratively, you define the kth term in here to be the bracket of the k minus 1th with the k minus 1th. So I think, if I remember right, our definition of bracket, right, is this, if I write this, I could also write this as L bracket L, right? I'll have to go back and find it. I'll try to find it. Oh, you're fine. I should have warned you earlier. I just golly. I'm pretty sure that L prime is L bracket L. I can't find it. Well, I guess he doesn't write that though. Well, anyway, I'm not going to fuss over it. Let me go on here. I'm a little bit uncertain there, but anyway. I mean, what does this mean? So. Pretty sure it's supposed to mean the span of commutators from, LK minus 1. All right, anyway, let me move on here. Lemma. Let's see here. I think I stated this lemma, but I haven't proved anything, so I wanted to just, take a second to try to prove something in here. This is lemma 4.4. I don't think I wrote it out last time. It's like Lie algebra. If L solvable, then every subalgebra and every homomorphic image of L are solvable. And then B, if L has ideal I and I and L mod I are solvable, then L is solvable. And then C, I and J, solvable ideals. Then I plus J, solvable ideal. So I think that the proofs of these are worth looking at because they use some of the isomorphism theorems that that we're kind of interested in understanding more, right? So let's see here. Here's the proof of A. So what do we want to do? Assume L is solvable, all right? So he says, let L1 be a subalgebra of L. What does that mean? So I think that means, among other things, that L1 with L1 is what? It's a subset of L1, right? So for to be a subalgebra, it should be, the bracket should be closed. And it's also it's a Lie algebra with respect to the same Lie bracket, right? He says it's clear that L. Okay, so let's see here how to say this. All right. Oh, I should, I'm a dummy. There's something I need to write out. How does the chain of ideals work? Is it, I think it's ideals, right? Derived series with terms. So the derived algebra L prime is the smallest ideal of L with an abelian quotient. And you remember the story here. We had I'll get it eventually. L contains the L1, which contains L2, and so forth and so on, right? If it's solvable, eventually you get to one of these being 0, right? That's the deal. All right, so what's he say here, his proof? He says it's clear that L1 of K, let me think about this. All right, so what do we know? Certainly we know, come on, I'm having more trouble with caps today. L1 is a subset of L, right? And we also know that, L upper bracket 1 is, well, let's use this notation whether or not it's standard. I'm pretty sure it is. So it's that, right? It's the derived subalgebra of L. So I think this is he's claiming he claims that L1, the kth derived series of the subalgebra, is a subset of the kth derived series of the algebra. So I guess at the, I mean, this right here is k equals to 0, right? So then what if you have, L1 comma L1? Well, he's claiming that that is a subset of, L prime, right? Of course, which is LL, right? Is that obvious? Yeah, I have a moment of doubt here, so let's work it out. How do you work it out if you're not sure about something? Pick an element, right? Okay, so let Z be an element of L1, 1, let's say. What does that mean? That means that Z is an element of the span, right? Of, like, let's see here, X comma Y, such that X and Y are elements of L1. But L1 is a subset of L, right? So, this, exactly, yeah, exactly. This is a subset of, this is pretty clearly a subset of the span of, let's say, A and B, such that A and B are just in L, right? I mean, of course, X and Y are in L, so they're also in here, and of course this could be bigger, but the larger point is that, well, yeah, duh. So, yeah, in fact, it's pretty obvious then that it's obviously true for 0, it's obviously true for 1. So, yeah, I mean, if I have L1 K is a subset of LK, then suppose that inductively. And this may be kind of a stupid use of induction, but suppose it's true inductively, then consider what would L1 of K plus 1 be? Well, that would be equal to the, L1K bracket with L1K, right? By definition. But it's really, the mechanics of it is that span thing we just did a second ago, but, right, I mean this, yeah, this is going to be a subset of LK, LLK. By the induction hypothesis, but also just by like a more basic theorem of linear algebra, right? Which is, if you look at the span of a subset, then it's a subset of the span of a superset of that subset. So, and of course this is equal to LK plus 1. And then, so there we go, proof by induction. All right. Okay, so anyway, so I'm spending entirely too much time on this. It should be clear that the the derived series for a subalgebra is in this way connected to the derived series of the algebra overall. But what are we assuming? We're assuming what? L is solvable, right? So we know that L of M is equal to 0, and so that implies that L1 of M is a subset of Lm, right? Equal to 0. The only subset of the 0 set is 0. So there you go. We proved that the derived series for the subalgebra likewise has to terminate in finite order. In fact, the same order at minimum. I mean, I think if, for an example, you could imagine that the subalgebra has a series which terminates earlier, right? Like a stupid subalgebra would be the 0 subalgebra, right? Or you could take the center of the Lie algebra or something like that. I don't know. But anyway, so the center of the Lie algebra has a trivial bracket, right? So its derived series is L1, L prime is 0 for the center of the Lie algebra. If I was to write this, Z of L prime, that would be 0. Because the center of the Lie algebra, the commutator bracket of it. Okay, anyway, so homomorphic image, he says that the rest of part A you get with apply exercise 4.1. What is that? Give me a second here, I'll tell you. I'm going to try to tell you. Come on, fingers work. What? Where'd that go to? Oh, dummy. Oh, there it is. Suppose, it's right in front of me. It's right above the lemma. Suppose you have a surjective homomorphism of Lie algebras. Show that, oh, okay, so the proof of this piece right here, it rests on proving the following, that the image of the first derived, well, the image of the kth derived series of the subalgebra is equal to the kth derived series of L2, and here we have phi going from L1 to L2 onto Lie algebra homomorphism. So he says if you can prove that exercise 4.1 right here, then the rest of part A follows. So let me think about that. Can Audrey, can I erase the top half of this proof here? Are we okay, or?
Yeah, you're good.
All right, so to prove this, let's just try to prove like half of it, okay? If Z is an element of L2K, right? What's that mean? Then Z is an element of the span, right, of let's say x comma y, such that, you know, x and y are elements of what? L2K minus 1, right? But the thing is that L2 k minus 1, right, is a subset of L2, yeah, which is equal to the image of phi under L1 by assumption. We're assuming that phi is an onto Lie algebra homomorphism. Uh-oh, I lost Audric. I'm all alone in a library now. It's a nice looking library. Is that West Alabama? Yeah, maybe. All right, so it's onto, right? So that means that there exists, let's say, well, let me be more specific here. Let's let z equal to the sum over, let's say, Cij, xi, yj, okay? For x sub I, y sub j, an element of L2, k minus 1, okay? I need to do that because it's supposed to be in the span. Fine. So, okay, there has to exist a sub I, b sub j in L1 for which what? Phi of ai is equal to what? xi, and phi of bj is equal to yj, right? For all I and j, because it's surjective, right? I can find these. All right. So what does this mean? This means that z, which is of course equal to then the sum over I and j of Cij, commutator of phi of ai, phi of bj, right? Welcome back. Long day? What's that?
Yeah, I just want to get coffee.
Oh. Why didn't I get coffee? I should have got coffee. I've been having tea before class lately. That is nice. But
I've become an espresso guy myself.
ooh, very fancy. So let me recap what we did, Audric. So I'm trying to show half of this at least. I'm doing half of exercise 4.1. I'm trying to show that the image is a subset of L2K, all right? So I'm picking an arbitrary element in L2K, and I'm trying to show that it's in fact, I guess I'm trying to show L2K is a subset of that. My bad. So, like I said, I'm doing half of it. Anyway, so if z is in here, that means z is in the span of these guys, which means it can be written as a linear combination of commutators of xi and yj, where xi and yj are from the k minus 1th derived series of L2. But that is a subset of L2, right? And L2 is the image of L1 under phi, which means I can find ai and bj, which map to respectively x sub I and y sub j. So then I can write my z as a linear combination of the brackets of the images, right? But what else? So what's my next step, do you guys think?
Well, you're saying the piece of I, piece of J, you take the brackets.
Mm-hmm.
It's a Lie algebra.
Right, exactly. This is a Lie algebra homomorphism, so it preserves the Lie bracket. We can take the phi out. And I'm going to do one more step. I'm going to take the phi out, but then I'm also going to use the fact that it's a linear transformation, so I can also pull it outside the sum, just to do myself less writing. So what I really have is phi of the sum of I comma j Cij bracket of ai bj. right? Using that phi is a Lie algebra homomorphism. Okay, well, what am I looking at then? So notice that here,
Oh, that's it.
and did I say L1? That ain't right. Where should they be? Oh, I guess that is true. They are in L1. Oh, curses. Aw, man. Dang it. That doesn't quite do what I wanted. See, because if AI, I mean, they are in L1, right? So this is, I mean, this is, at my current level of argumentation, this is just an element of what?
You have that one.
Yeah. This is an element of L1, L parentheses 1, 1. Or if you like, L1 prime, right? But what did I want?
You want it to be an L1K.
Yeah, I want it to be an L1K. So the argument's not... So, but I do think that I've shown you the heart of the argument here. How do you fix this? Any ideas, Audric?
Not so far.
None so far. Okay. So I think that the idea of the argument is not wrong, but what you have to do is, instead of just trying to calculate it, all right, as I've done, instead assume inductively. Assume this is true inductively.
Oh, the mapping?
Yeah, I mean, for k equals to 0, it's true. That's surjectivity.
Yes.
Okay? So suppose it's true for k. Show that it's true for, or you might even need to do strong induction, but I need the inductive step. So it's like this idea paired with the inductive step is how you prove that exercise 4.1, I think. That's my current speculation on the matter. Of course, I could be wrong. Anyway, so that's part A. Let me look at part B here, see if I want to get into it. No, I didn't have coffee, so I'm not going to try part B or C. But part B and C are, let's see here. Well, Well, I'll just tell you, after some argumentation, you get to the following. L well, there's a few different moving pieces in here. Can I erase this?
So I was reading to see if I could put the argument together. What's this?
For part, can I? I'm gonna.
Yeah, just here, yeah. Or the left. That's fine.
I mean, can I erase my flawed proof?
Yeah, it's fine. You did put it into the it's fine.
Okay. All right, so for part B, he points out if we look at L mod I, the kth derived series of that, you can show that that's equal to the quotient of the kth derived series plus I mod I. So he says if L mod I is solvable, that implies, of course, L mod I for some m, the mth derived series is equal to 0, right? So if that's the case, that implies that what? That implies that L m plus I is equal to I again. In other words, the mth derived series of L is a subset of I. All right, let's see here. So we're like, what was part B? L has an ideal I and L mod I are solvable. All right. Okay, so we almost have it. We've got that, you know, this is a subset of I. All right. And we know that I is solvable, right? But that's not quite, that doesn't quite do it directly, right? But he says what you can convince yourself of, or prove from the directly from the definition, is that if you take this guy and you look at the kth derived series of that, it's pretty cool. That works out to the m plus kth derived series. And so that would be a subset of I of k.
And are we saying that I and k is 0? So it's
Right, and then there has to exist a k such that I of k is equal to 0. Therefore,
that means a subset.
then that would mean that L is solvable as well at order m plus k. Yeah. So. All right, and I'll skip part C. I've tortured you guys enough for this here today. Remember, we also had, you said there's a unique solvable ideal containing every other solvable ideal, and that largest solvable ideal is called the radical of L, right? So radical of L, let me erase these things, and definition, radical of L is largest solvable ideal of L. All right. And for L not equals to 0, all right, finite dimensional, the algebra L is said to be semi-simple. All right, semi-simple. What? If it has no non-zero solvable ideals. In other words, if the radical of L is 0. All right? And we will, hopefully before today is done, define what we mean by simple. All right, but we're not quite there yet. One more lemma here. Lemma 4.7. If L is a Lie algebra L mod rad L is semi-simple. I think this one is worth taking a few minutes of our time to look at because it touches back on that correspondence that I kind of glossed over, all right? So here's the proof. All right. He says, let J bar be solvable ideal of the quotient L mod radical of L. All right. He says, by the ideal correspondence, all right, there is an ideal J of L containing rad L. All right, such containing rad L. So it's such that rad L is a subset of J, all right? And J bar is equal to J mod rad L. Okay. But the thing I just erased, let's see here. By definition, rad L is solvable, right? So what do you have? J bar and rad L solvable, right? J bar by assumption, radical by definition, largest solvable ideal, right? By the lemma we just proved, part of, right? I think this is the part of the lemma we actually did prove, the first part of it. Look at what we got. We've got the thing we're quotienting by is solvable. The quotient together is solvable. So therefore, J is solvable. Right? But then J is contained in rad L. So what does that mean? How can you have, you know, the only way Oh, what is that? What does that mean about J bar? What does it say about J bar? If J is a subset of radical L, then this is the what?
Oh, it's just
Right. It's the what? Well, it's, yeah. I mean, but this is specifically what if we're looking at a quotient and you've got something which is a subset of the thing you're setting to 0, then that means that J bar is 0 because J is a subset of the radical.
Yeah.
So, but then what does this mean? Oh, this means that the only solvable ideal of the quotient is the 0 ideal. So the only solvable ideal of this quotient is the 0 ideal. That means this is semi-simple. In other words, the radical of L mod the radical is in fact 0. So if you want to take a given Lie algebra and make it semi-simple, mod by the radical. Then you've got a semi-simple algebra. All right. That brings us to section 4.2, which is on nilpotent Lie algebras. All right. So let's talk about nilpotent Lie algebras. And I'm going to erase I think I'm going to erase everything here except for the top corner, because I think we're going to want those in a minute. Oh yeah, sure.
I was missing like I was able to put it together, but I was missing the like tiniest of corners in the far side of the board. A little more to yeah.
How's that?
Yeah, good. Yeah.
Okay, cool. Where was I? Oh yes, nilpotent. What do we have to say about nilpotent Lie algebras? Well, so this is called the lower central series of L. And here we go. L1 is equal to L prime, and LK is the bracket of L with LK minus 1 for K greater than or equal to 2. And he says, then L is containing L1 is containing L2 is containing ... And he says, as the product of ideals is an ideal, LK is even an ideal of L. It's not just an ideal of LK minus 1. So in fact, here LK is ideal of L for all K, okay? And he says the reason for the name central series comes from the fact that LK, the reason they're called central, reason for that is you can prove that the quotient of LK by LK plus 1 is, it's contained in the center of the quotient of L by LK plus 1. All right. All right, so what do you think the definition of nilpotent is going to be? If for some m greater than 1, we have what? We have L to the m equal to 0. The difference is, so the difference is the parentheses are, notice the difference. Like just, see the difference here? Compare this, right, to this. For the kth
You're bracketing the same thing.
oh yes, for the parentheses one, we're bracketing the same thing. For the no parentheses one, the lower central series. So this is the lower central series, this is the derived series. Okay? Derived series, lower central series. They are different. Although interestingly, they start out the same, right? L1, you know, we do have this. L prime is equal to L parentheses 1 is equal to L without parentheses 1. And they're all equal to the bracket of L with L, which by definition is the span of commutators x and y such that x and y are elements of L. I mean, there you go. That's why if you're trying to understand the distinction between these concepts at level 1, it's not a good place to try to understand the distinction. You got to get to at least 2 to see the difference. So that's a so-called nilpotent Lie algebra. An example. Oh, an actual example. What do you know? Example 1. He's like n f. So what are these strictly upper triangular matrices over a field F is nilpotent? So let's see here. So we could look at it for a second here. This would say we're looking at 3 over the reals, right? We're talking about the span of what? Strictly upper triangular. So you're looking at 0, 1, 0, 0, 0, 0, 0, 0, 0, or what? Or in less annoying notation, E12, E13, E23, right? And if we calculate the, what is L prime here? If this is L. So it would be the span of, E12 with E13, E12 with E23, and E13 with E23. You can prove that as long as you look at the span of all distinct commutators, that is it. I think that's the sort of thing that may be more spelled out in Misra's notes, if I remember. I need to look at them again, but sorry, I didn't get you a copy yet. If you're interested, I can get you a copy. So how did those work out? You guys tell me, what was the formula? What was the commutator of Eij, EKL? How did it work? What was it? It was Kronecker delta. Golly, was it JK? EIL minus Kronecker delta IL EJK? You'll have to look.
No, it's Kronecker JK, EIL minus Kronecker IL, EKJ.
EKJ.
It's not JK, it's EJ. Yeah.
Well, I was almost right. So are any of these non-zero? So the middle indices, well, these middle indices match. So this is going to give us E13. Let's see here. These don't. Those don't. I think it's just E13. And then, of course, if you is that right? Yeah, okay. So what would L, so this is L prime, this is also equal to L1, it's also equal to L parentheses 1, right? So in this case, L parentheses 2 would be the bracket of what? Of L1, L prime, right? That would be 0. So it's solvable. So it's solvable. I mean, I can see that it's 0 because you're taking the commutator of one-dimensional thing, right? The bracket of E13 with E13 is necessarily 0. What's L2 here, though? So there you're looking at, the bracket of L with L1. So I guess you're looking at the span of what? E12, E13, or E23, E13. Which I think is 0. So this is not a great example in terms of seeing the difference between solvable and nilpotent, Because I think here this is also nilpotent at the same order as well. All right. Well, let me read his claims. What else can we say here? He says, furthermore, any nilpotent Lie algebra is solvable. Oh. To see this, show by induction that LK you can show by induction, all right, that LK is a subset of L without the parentheses K. So this means that solvable, excuse me, the other way around, right? Yeah, nilpotent implies solvable. These are different ideas, so rest assured that the other implication isn't always met, right? He says, okay, so there are solvable Lie algebras which are not nilpotent, and the standard example is just upper triangular matrices over a field of n greater than or equal to 2. All right. So let's see here. Solvable but not nilpotent. Upper triangular matrices for n greater than or equal to 2. Another is the two-dimensional non-abelian Lie algebra. That's a Lie algebra which is solvable but not nilpotent. Let's look at the n equals 2 case of this, because he says it's a counterexample even at n equals to 2, right? That should be pretty easy to calculate. Let's try that. Okay. So B2, what's B2 here? So B2R, my bad, B2R, we'll take that to be our L. So that is the span of E11, E12, E22, all right? So a typical thing in here looks like A, B, 0, C, right? That's a typical upper triangular matrix in the span of these three. So can we calculate what is the, what is it, Audric? Am I not, you look befuddled.
Oh, I'm looking back at the last, I'm just putting together the last example, sorry.
Oh, I'm sorry. This is miserable way to do things.
No, don't worry, like I go back and just like study the textbook myself.
Okay, so let's see here. So we want to calculate the brackets, right? E11, E12, what's E11, E22, what is the other bracket to think about? E12, E22, right? Those are the 3 choose 2. There's 3 choices. So are any of those non-zero? Oh, this one is. This is E12, isn't it? Yep. This one here is 0. This one here is also E12. So this tells me that L prime is in fact the span of E12, right? And so that's, if I look at the bracket of L with L1, what do I get? We're talking about the span, right? Of like E11 with E12 or E22 with E12, right? Because my L prime, I only have E12 to pick from in the span, in the sense of spanning, but L1, L itself, I've got E11, E12, and E12. E12 I ignore because I know the bracket of E12 with E12 is 0. And what is this equal to? Well, that's E12, and that's E12. So there you go, which is what? L1. So this is L2. So what's L3? L with L2, also known as L with L1, which is also known as L1. In fact, Lm is equal to L1 for all m greater than or equal to 1. Therefore, the strictly, well, not the strictly, but the upper triangular 2 by 2 matrices they're not nilpotent. But they are solvable, because if you were to calculate L parentheses 2, right, which would be L parentheses 1, L parentheses 1, you're looking at what? You're looking at the span of the commutator of E12. This is 0. Because you're essentially taking the commutator, you're taking the product of a one-dimensional algebra with itself. So that's 0. So there you go. There's your example. Solvable, yes for B2R. Nilpotent, no. Solvable does not imply nilpotent. Which is good, because otherwise it would be really silly to have a separate section devoted to another name for the same thing, you know? Solvable does not imply nilpotent. Although it's possible, right? As we just saw for the 3 by 3 strictly upper triangular matrices, there we did have nilpotent and solvable. And these are actually, both of my examples today have been 3-dimensional Lie algebras, if you think about it.